All right. We are going to introduce the sorting algorithms in chapter 23. Do you have any questions on the assignment for chapter 22? Okay. All right, I'm going to move on now. You can email me if you have questions. And you can also talk to me after the class today. But please be reminded the due day for chapter 22 assignments is tonight. All right, so now we are going to introduce sorting algorithms in chapter 23. We already know how to sort things. In chapter 7, we introduced selection sort. In the Java API, we have the sort method in the array and in the list. And also, we have the tree set and tree map. So they're using the sort mechanism to maintain the elements in the set and in the map. Sorting is frequently used in programming. So it is very important. It's a common task. So it has been well studied. There are many different ways to sort things. We're going to study it today is to look at different ways to sort and see the how we develop efficient algorithm from using the sorting algorithms. So there's two purposes here in this chapter. First thing is sorting is very important. So it's very well studied and we need to know all the classic sorting algorithms. And the second thing is we're going to study the algorithm design, analysis through sorting algorithms. Now you can sort anything, any objects, as long as you know how to compare the elements. So you know how what's the criteria to sort. So you can use either using the natural order and from there the comparable interface, or you can specify a comparator. All right, so now we're going to look at this insertion sort. We already have selection sort, so just recall that using selection sort, we have a list of items and we always first find the smallest one and swap it with the first one, and then continue the same process in the remaining list. For selection sort, that's the strategy. So very natural. And now there are many different ways to sort it. So here's another one. It's called insertion sort. Insertion sort works this way here. So let me get the size increased to 10 elements. So I'm going to reset it. So this is the, you can reset it and to get a different random numbers in the list. So here, I'm going to reset it here in this way here. This is my list. So, all right. So here we're going to start from, the first one, it's already assumed it's already in order. It's 86. Oh, no, the next one is 88. All right. So that's already there. This is the already the largest in the sub list. So this is in the right order. Now, next we look at 54. We are going to insert 54 in this sub list. The sub list at the beginning of this entire list, it's already sorted. So we're going to insert it. What are we going to insert it? And 54. So where are you going to put it? It's going to be here at the beginning. So this is, you do have to do some shift now. So let's see, this is the shift, and then 54 is here. All right, so now these three are sorted. Next, 12. So this is going to insert it here. So let's look at 12. We're going to insert it, okay? At the beginning, this is 12. And now it's 40. So 40 is going to insert it between 12 and 54. So here. All right, so now you can continue. And so this next one is 40 is going to be inserted between this 40 and 54. So you know the process and how this works. Now, this is the insertion sort. So eventually when we get to the very end, so, and then we're going to insert it, and this, the last one, into the sublist already already sorted. So this is going to be all the way going to the end. So that's the insertion sort. So what's the time complexity for this insertion sort? All right, so we're going to analyze it, and you're going to see how we're going to implement it. And so this is the code here, and to implement it, let's look at the time complexity. It's Tn, so this is time complexity function, and with the input size n. So the first one, if you look at this list is from here, and so this is the first one here. So the first is, so let's reset everything here. So the first is already sorted. So this is, we're going to start it, actually start from the second element and see if we need to insert it. So this, and what's the time for this is, if you look at this, is the code is, we write this code. It's this is a for loop, it's this, and starting from this I is from index 1, it's not 0, 0 is already there. So we're going to start from 1 and all the way to the last one. And so we're going to insert this list brackets I into a sorted sublist and here. All right, so here it's the for loop. And now when you do this insert, and you need to write another for loop. So another for loop is right here. You're gonna see this is because you have to do a shift insert, right? So this is the in the worst case. And so what's the time? You can see this is going to be the time is the I, the index I, so where the I is. All right, so the time complexity, if we add all this together, so this is the first, that index I, so that's the time. It's I put a 2 right here. It's just like you have, this is the time, it's the you have to move things, shift, right? And then the insert here. So that's the time. So I put it there. And you have to compare things. How do you shift it? And you have to compare and then shift. So if necessary, shift, otherwise don't shift. So that's why this to compare and shift, move. So for this, at index I is 1, I is 2, and all the way the last is I is index is n minus 1. If the size is n and the last index n minus 1. All right, so add all this together and you can see that, and this is the one. We're gonna ignore the non-dominating items and ignore the constants. So here is we are getting this is order of n square time. So the time complexity for insertion sort is order of n square time. All right, so let's look at the next one here. We're gonna look at another way to sort is called a bubble sort. Now, bubble sort works this way here. It is, so again, I'm gonna set this to 10 elements and reset it. All right, so the bubble sort is this. You're gonna comparing neighboring two elements. If they're already in order, and no swap. All right, so here, no swap. All right, but this not in order, swap it. And this is not in order, swap it. 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 So finally, you have this 83 is in the right place. So this is the it's a bubble sort. It's also called the sinking sort. So you have the last one is going to be the largest one after this one phase. So this is one phase. You can see it. You're going to write in a loop. It's one loop, right? So it's not done yet. So we'll continue. The next is from the beginning here. Let's see if we need to swap. Yes, 79. 79 is large. So comparing swap, no swap because this is 82. So now, and the next is 82 with 66. All right. So after this, and 82 is in the right place. So you can see the process. It's called a bubble sort. All right. So here, and we write the code and to implement it, the algorithm, and then the code. So the algorithm here is this. You have phases. So it's a loop. It's the outer loop, and the inside loop, you comparing the neighboring elements all the way to the end. So this is the another loop, and you can see this is going to be order of n squared. So if you just do the number, put all this together, it's going to be this order of n squared time. So that's called a bubble sort. It is order of n squared time. So just to look at all this time, all the complexity, we have selection sort, order of n squared time, insertion sort, order of n squared time, bubble sort is order of n squared time. Can we do better? Yes, we're gonna have another approach in sorting. The next one is, it's called merge sort. All right, so this is the design approach we have very common in algorithm. It is called divide and conquer. So we are going to do this. It's called divide. See, we can do that. And that's something you're going to use in the future when you design some non-trivial algorithms. You can think about it. Hey, can I divide the data set into two parts and solve each part, and then combine the result to achieve the overall result. So this is the list, for example, just to have, this is the 8 numbers. We're going to divide it into 2 parts. So the first part and the second part. Further, we continue to divide it until we cannot divide it. Divide. Until now, there's a single element here. You cannot divide it. Also, now you're going to merge. So 29 is 29 here. 5, 4 is becoming 4, 5. All right, here 29, 5, 4, we merge them together. So becoming 2, 4, 5, 9. And here, and this 2 sublists, 2, 4, 5, 9, and here's 1, 6, 7, 8, and merge them together, and it becoming, and this. Everything sorted. So this is divide and conquer. All right, so this is the idea, and let's see if we can write the algorithm to describe it. So here is the algorithm and implementation. So I'm gonna just look everything, and just to give you another visual diagram, here is the merge sort overview. So here we can have all these different numbers and reset, reset, reset. All right, so now let's do this. This is how it works. Divide. All right, and then you work this on this two sublists. All right, work on those two sublists recursively. You can see how it further divide, 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 and until you cannot divide, then conquer, conquer, conquer. All right, combine it together. So here, and that's what we're gonna apply this merge sort on this first part. And so this is sorted, and you apply the merge sort on the second part, and this is sorted, and then merge them together. So eventually everything is sorted. All right, so everything is sorted. Okay, so here is the code. You can see it. It's the merge sort, and you sort this list. So what you're gonna do is you have divide the two. So the first half and the second half. Okay, so this is the first half. So the first half, you're gonna create this with the half of the size, and you're gonna copy from this list and copy the first part into the first half. So copy the list and into this first half. All right, and recursively apply merge sort on this first half. All right, so let's get the second half. So this is the second half. So the second half, this is the size for the second half. So this is the second half array created, and then we apply this. This is the array copy. So from the list, and copy the second half into this second half right here, second half. All right, merge, sort the second half. So all this done, and now finally we have this two sorted sublists. So we're gonna merge this. Merge, call this method, and merge first half and second half, and then back to this original list. All right, so this is merge. So here is how you're gonna merge the two. So this is the algorithm to merge the two. All right, what is the time complexity? So look, the time complexity, it is this. I'm going to first look at the time complexity. You can see this is the sort here. Original, you're going to divide into first half and second half, and recursively apply this merge sort on the first half and second half, and then finally merge the two sorted sublists. So this is time complexity. It's Tn, it's the overall time. And so you divide it into two parts, right? So this is two parts. You have to do it recursively on the first part and the second part. All right, and then there's a time to merge the two together. So you merge the two together. And so there's a time here. All right, so what is the merge time? All right, the merge time happens to be linear time. It's a linear time. So if you go with this and eventually expand this and solve it, it's the overall time. It's going to be order of n log n time. All right. So we are going to look at this. How do you merge the two sorted sublists? So you see, this is the first half. It's sorted. And the second half is sorted. Now we need to merge this. Okay, you can reset the numbers with any numbers you like. And so, but look, anywhere, whatever you do with this reset, this is sorted, the first half, and the second half is sorted. So now we're gonna merge the two together. So how you do merge this? Well, you have this is the current one, current two point to this first half sorted sublist, and the second half sorted sublist, and this is going to be new. Okay, current three. All right, you're going to compare the element at current 1 with current 2, whichever smaller goes to current 3. All right, and then 34 is going to be here. And then 37 is going to be here. And 39 is going to be here. Okay, now is 42. 42 is less than 50. See, that's how it works. All right, you see how this is going to work, continue in the same process. So you're going to see eventually, and everything, it's going to be sorted in the big list. All right, so what's the time? This is linear time because you have, this is all this 3 pointers here. Current 1, current 2, current 3, they all move sequentially. Every time, every step, you have to move one time. So that is the linear time. It's a linear time. All right. So it is I think I put a 2n minus 1 here. It is because you have a compare. You count the compare as one time, and you count the assignment as another time. So you have this 2n. So here is this is yeah, it's 2n. So the to merge 2 sublists, it takes at most n minus 1 comparisons, and n moves. So that's 2n minus 1. So that's it. So actually, it doesn't matter. You can just put n here. So we know that the constant and the small items doesn't matter. So this can be simply just put it all of n here. So when you do this analysis, you get all of n log n. So if you continue to do this expansion, and you can find out this is how it works. This is the get this order log in, and the trick is every time you're going to cut it the size, smaller size by 2 by 2 by 2 by 2. So that's log in count small. All right, so this is very good, very nice algorithm and very efficient algorithm. It is actually used a lot in the API, in the Java API, and the sort method is implemented using merge sort. Merge sort is efficient, all of n log n time. Comparing it with a selection sort, insertion sort, and bubble sort, this is very, very fast. All right, there are a lot of other ways to do it. So you need to know all this classic sorting algorithm and be able to describe it. Hey, what is selection sort? So what is bubble sort? What is insertion sort? What is the merge sort? There's another one. It's also very classic. It is called a quick sort. So let's get into this next one. It's called a quick sort. Quick sort. All right, so what is a quick sort? So by name, it's quick. It's very quick, right? Well, that's just the name. It's called. It has a very good overall performance, and the average time its quick sort is very good. It is out of n log n time. So this is the how it works. It works as this way. We're going to have a list. We're going to use a pivot. So the pivot is any number you choose from the list, but you're going to choose, normally we're going to just choose the first one now. All right, so here, you're going to choose this pivot, the first one here in this list, and use this pivot and to partition the list into this 2 sublists, list 1 and list 2. All right, so everything in list 1 is less than or equal to the pivot, and everything in list 2 is less than the pivot. I'm sorry, everything in list 2 is greater than the pivot. So everything in list 1 is less than or equal to pivot, and everything in list 2 is greater than the pivot. All right, so here is this, and the algorithm can describe it as this. So here's quick sort the list. So if the list size is greater than 1, so we're going to choose a pivot. So partition the list into list 1 and list 2 such that list 1, so elements are less than or equal to pivot, and the list 2 elements are greater than pivot. All right, so list 1, list 2. This pivot is in the right place. You don't need to touch it anymore. Don't do anything with pivot. So now apply quick sort on list 1 and list 2. Recursively. So this is the algorithm. All right, so the if you expand this and implement everything, and so here we're going to have this. Eventually, we have this as the code here. Quick. All right, but now this is the one big part is, hey, how do you do the partition? How do you do the partition? So what is the way to do partition efficiently? So we're going to look at this partition as this. So here, if you look at this pivot, so this is 5. So this is the end result. So now you partition it and into this 2 sublists. All right, so 5 is going to be here. Okay. All right, and if what you do with this list, so this one here, so you have this 5 here. So now you have 4, 2, 1, 3, 0. Let's look at 4, 1, 2. So 4 is here, and it's going to be like this, and so it's going to be 1 is empty, and the other one is this. So this is the this one here, yeah, 4, and here is 0. It's this right here. There's nothing you can do with 0 here, and this, and here, and D here, it's like this. So here's 2, and so you have 1, 3. Okay. All right. So this is the you can see this is not a, this is a pretty much, it's like even partition. So it's 5 somewhere in the middle, but the next one here is 4 is not. I think this is just 4 should be right somewhere here. It's going to be somewhere here. It's I need to fix this. It doesn't look right. Okay, 4 is here. So this is for 0, 2, 1, 3. It's going to be like this, 0, 2, 1, 3 here. 0 is here. And now for 2. So this is like this. Okay, let's look at this animation here. So how we do this partition, and for this partition is, we're going to choose this. You can any list, so any list here. So any list, okay. All right, so let's just use this list now. 36 is the pivot. So how do we do this? We're going to have this, the index, low and high. So this is going to be, so this is the pivot, and this, it's the result now. You're going to see this is 36 is going to be here. So everything here before 36 is less than or equal to 36. Everything after 36 is greater than 36. Let's try it again. So for 47, so, and if we perform this partition and see what happens, this is the pivot, 47, and this is going to be 47 is right here. All right, see how it works. Let's look at the animation down here. So this is the animation. If you have this, is 37 right here, it's the pivot. This, it's the low, and this is the high. All right, so this is we're gonna move this. We're not doing anything with the pivot now, stay here. So here, we're gonna look at this, comparing this 38 with 37. So, this is something we're gonna have to move to the second part, because 38 is now greater than 37. All right, so look at 61. Oh, this 61 is greater than 37. It's going to be stay. All right, so now you can see that we're going to move this high to the next one, see what happens. All right, 72, still high, still greater than 37, and 40 still greater, and 47. Okay, now 22. Okay, that's fine. 22 is less than 37. So we need to do the swap with 38 with 22. All right, so now, and we're gonna move low to the next one. All right, this is less than 37 state. This is gonna be moved. Okay, 45. And this is 38. It's right here. It's greater than 37. We're gonna move this high to the next one here. 39 still higher. All right, so now 14 should be moved, right? And 45, they should be swapped now. So, all right, so now we continue and low, move to the next one. It's going to be moved, and next one stay, and here. All right, so this is going to be swapped. All right, so now continue. So this is going to be moved, and this is going to be, this is stay, but now you see what happens. Continue, and continue right here, they're close. So everything exhausted. So now we're gonna swap 37 with pivot. So the pivot is gonna be here. All right, so this is how we do the partition. And as you see, the time complexity, it's linear, it's order of n time, the size of this list. So what is the overall complexity? So I'm going to give you, the first thing is the worst case situation. In the worst case situation is this pivot, it doesn't divide anything, it stays in the extreme first or the last one. So your two sublists, one is empty and the other one is just everything's remaining. So this is the one smaller than the previous one. You can see that situation. That's going to be extremely bad situation. It's in the worst case. So what's the time complexity? You're going to add all this together. It's order of n squared time. So this is all the sublists like this. All right. But the average case, it's actually really good. If you do all this probability analysis, and you find out, and the average case, it's something like this, the best case. It's like every time you divide it into evenly two parts. All right, that's the mathematical proof. It is, it's beyond the scope of this class, but you just have to accept that this is the proof we have. It is give you the average time. It's order of n log n time on average. Okay. So that is very good, and it's average time. So that's still it's a good algorithm. Okay. Quick sort. So you need to be able to describe, hey, merge sort and quick sort, what's the difference? Merge sort is, it doesn't matter, you just cut half. All right, but quick sort, you use a pivot to partition the list into two parts. The pivot is going to put in the right place. All right, and if you do all this careful coding, look at the how this is the implementation, you can see this, the merge sort, you always have to introduce additional memory. when you merge things. So you have to have additional memory to put the result in the new memory space. And the quick sort, you don't need to have additional memory. You just have this pivot, you work on the original list. So that's the benefit of the quick sort, and no additional memory is needed. All right. So I'm going to get into next very interesting algorithm, and this time we're going to use a little bit data structure also, and for this algorithm. So this is called heap sort. Okay. So let's go to the next. It's called heap sort. Okay. All right. We are familiar with this term heap in object-oriented programming, and the heap is the memory space to store objects. All right, so that's one use for this term heap. But here, in this context of heap sort, and heap is a data structure, it is different from that memory space for objects. So what's a heap data structure? And a heap is also known as a binary heap. Okay, so here, look at this binary heap. So the heap is a data structure, it's a complete binary tree. It is a complete binary tree. And that's the first thing. Okay, now what is a complete binary tree? Complete binary tree looks like this. So this is a complete binary tree. Binary tree. So the binary tree, it's a tree. Tree is in computer science, binary tree is you have two branches. Okay. So, and each one has at most two branches. So the first is called the root, and then you have this left subtree and right subtree. So, and then so you have the leaf. Leaf does not have any children. So this is the data structure in computer science, and this is the binary tree. It's like this binary tree. All right. So what's a complete? It's every level is filled except at the last level. The last level, if it's not filled, so they're all filled completely to the left. So this is a complete binary tree, A, and B is a complete binary tree. But the C is not, because look at this C. That's a little bit strange. I should have not have this one guy. Okay. Okay. So, okay, I see something here. This is a mistake. There's no 32 here. And there's no 29 here, so I need to remove this. 32 here, 29 here. This is should not be here. All right, this B is not a complete binary tree. There's no 32 here. This is B is complete binary tree. So everything pushed to the last level is to the left. And this one here, it is not. So there's no 29 here. So there's one space is open right here. Okay, so there is no. This is not. So every level is filled, and so this level is not. And so this last level it's filled. It has to be pushed to the left. But this is right here. See, this is empty. All right. So this is A is complete binary tree, and B is complete binary tree. So again, by definition, a complete binary tree is every level is filled except the last one. And the last one, if it's not filled, and they're all filled to the left full. All right, so now we're gonna go look at this. Another property here is this property here. It's called a heap property. So the first one is a shape property. It's a complete binary tree. And the second one is the heap property. is each node is greater than or equal to any of its children. So here, look, this is 42 is greater than 2 children here, and 32 is greater than all this, 39 is greater than all this. So here is, this is not, 39 is here. Look at 39, 39 is less, it's great, it's less than 42, so this is not. So, all right, so look at this animation for the heap. So this is our heap right here. So this is fine, it's a heap. So this is the, it's a complete binary tree, and this is the 89 is the largest, and 42, so larger than this two, 80. All right, now I'm gonna add something. So I'm gonna add 57. So how do you add 57? You're gonna put 57 right here at this open spot right here, 57 right here. And then you're going to swap with its parent if they're not in the right order. So look, this is this. Okay, all right. So this is still a complete binary tree, and it is now in the right order. All right, let's do another one here. We're gonna add this time at 89. So where do you put 89? Put right here. 89 here. This is the spot here. You're gonna put 89. So it has to satisfy the complete binary tree. So, and now swap it if necessary. All right. Okay, after this, we have this new number added to the heap. And the result of this is still a heap. It's a binary, complete binary tree. It has in the right order, everything. All right, so we're gonna use this data structure to develop efficient and heap sort. We're gonna introduce this in the next class. All right, any questions? Any questions? All right, if you have questions, please stay, I'm here. All right, otherwise, you may feel free to leave. So I'm going to stop recording now.